Okay, hi guys. Today we will do tutorial number 5. Okay, let's quickly go into question number 1. So we have a steam power plant, okay, producing dry saturated steam, okay, and the feed water enters the boiler, okay, at a temperature of 38 degrees. So very simple. Step A or step 1, okay, is to write down your conservation of mass. In this case, m.1 will be equals to m.2, which is equals to 2.8 kg per second. Okay? Then the next thing to do is to write down your H1 and H2. So in this case, H1, okay, it is feed water. So we assume it to be compressed water. So the property of compressed water will be the same as saturated water at the same temperature. So in this case, this will give me 159.1 kilojoule per kg. Okay, next H2 will be your dry saturated steam, which is equivalent to Hg at 30 bar. Okay, and from the saturated water and steam table, this will give you 2803 kilojoule per kg. Okay, so that's it. We are ready to write our steady flow equation, which is Q dot in plus W dot in plus M dot 1 H1 plus GZ1 plus C1 square over 2, okay, equals to Q dot out plus W dot out plus M dot 2 H2 plus GZ2 plus C2 square over 2. Okay, so in this case, all your potential kinetic on eligible, okay, can and there's no work in given by the question, and there's no work out, so we just have to fill in the rest of the values. So Q dot in is what we want to find, okay, M dot 1 is 2.8, H1 is 159.1, okay, which is equals to Q dot out, which is given to be 350, okay, plus 2.8 times H2, which is 2803, okay, and from here you can calculate your Q dot in, which is equals to 7753 kilojoule per second. Alright, so this is very simple for part A. Next, let's move on to part B. Okay, so for part B, in this case we have this again, the steam from the boiler is superheated to a temperature of 450 before entering a turbine. So we are working with actually a turbine. Okay, so the steps are pretty much the same. Okay, so we're going to write down your conservation of mass, which is m.1, which is equals to m.2, which is equals to 2.8 kg per second. Okay, we are using the same values because the steam is from the same boiler. Alright, and then now we have H1, which is equals to, for one, it is actually a superheated steam, correct? So we got to go to the superheated table and find out the H at 30 bar and 450, and from the table it will be 3343 kilojoule per kg. Alright, and then we have our H2. H2 in this case we are given to be wet steam at 0.42 bar. So wet steam, we got to use the wet steam formula, which is 1 minus X HF at 0.42 bar plus X Hg at 0.42 bar. Okay, so we plug in the values. 1 minus 0.95, okay, dryness fraction is 0.95 given by the question. 323 plus 0.95 times 2638, and this value over here will give us 2522.25 kilojoule per kg. Alright, and then now again we are ready to write our steady flow equation, okay, which is Q dot in plus W dot in plus M dot 1 H1 plus GZ1 plus C1 square over 2, which is equals to Q dot out plus W dot out plus M dot 2 H2 plus GZ2 plus C2 square over 2. Okay, Can, so we will cancel all the unnecessary terms. In this case, there's no Q in, no W in, no GZ1, no C1 square. Okay, no GZ2, no C2 square. Okay, so we plug in the remaining values. Okay, and we can solve our W out, which is gonna be 2168 kilojoule per second. Okay, so this is all for question number 1. Okay, next question number 2. Okay, almost the same format, but in this case we have a superheated steam. Okay, enters a turbine and leaves at wet steam. So for part A, same thing. Okay, m dot 1 will be equals to m dot 2, which is equals to 2.8 kg per second. Okay, in this case for stage number 1 is superheated steam, so H1 will be H from the superheated table at 40 bar and 450 degrees Celsius. Okay, so from the table you can get 3330 kilojoule per kg. Okay, H2, okay, this is again a dry wet steam, so we use the wet steam formula at 1.2 bar. So 1 minus X HF at 1.2 bar, okay, plus Hg also at 1.2 bar. Alright, so this will be 1 minus 0.95 times HF at 1.2 bar. Okay, let me see. The question here is 1.2 bar. Okay, but my working indicates that it is at 1.25 bar. Okay, never mind. We will follow the 1.2 bar. Okay, so this will be 439 plus 0.95 times 2683. Okay, so you calculate a H2, this will be 2572.96 kilojoule per kg. Alright, and so we are ready to apply the steady flow equation. Okay, we will cancel all the unnecessary terms. Q dot in don't have, W dot in don't have, GZ1 don't have, C1 square don't have. Okay, and GZ2, C2 square don't have. So we'll plug in the remaining values. And our W dot in will get alright, so that's it for part A. For part B, the same steps. Okay, so in this case m dot 1 is still equals to m dot 2, which is equals to 2.8 kg per second. Okay, H1 will be 2572.96 kilojoule per kg. Okay, this H1 is from your previous part because it is said that the wet steam, okay, the wet steam exhausted from the turbine enters the steam condenser directly. Okay, so the H1 for part B will follow the wet steam H that you calculated from the previous part. Okay, H2 will be HF at 1.2 bar, which is 439. Okay, and we are ready to apply our non-flow equation. cancel all the unnecessary terms. And we'll now plug in the values. Okay, that's all for question number 2. Okay, for question number 3, it will be the same thing. Okay, so why am I going through this tutorial very quickly? Because I want to show you that it's actually the same step. Okay, basically chapter 5 in the exam, you have to score chapter 5. They are the same steps. You don't even need to know about the system. Alright, so part A, same thing, step 1, m.1 equals to m.2 is equals to 1.2 kg per second. H1, in this case, you are given as compressed water, right? So it will be the same as saturated water at the same temperature, 117.3 kilojoule per kg. Okay, from the table. And H2, it is wet steam at 5 bar. So use the wet steam formula at 5 bar. So the dryness fraction is given to be 0.68. And your H2 calculated will be 2074.12 kilojoule per kg. Okay, so once you are done calculating M1, M2, H1, H2, okay, we can proceed to using the steady flow equation. Okay, so this is your steady flow equation. We will cancel all the unnecessary terms. Don't have W dot in, don't have GZ1, don't have C1 square. Okay, don't have W dot out, don't have GZ2, don't have C2 square. Then we plug in the remaining values. So your Q dot in will be 2378.18 kilojoule per second. Alright. Okay, next we move on to part B. Okay, part B a bit more special. Okay, so as we have gone through in the lessons, okay, this is a mixing chamber, so we got to slightly modify the equation a bit. Alright. So today it is said that the wet steam from the boiler in 9A is mixed with cold water at a temperature of 28 degrees. Okay, so there's two sources of input. So for the conservation of mass, what goes in must come out. m.1 plus m.2 must be equal to m.3. Alright, so in this case m.1 is not given, m.2 is 1.2, m.3 is given, is not given also. So this will form your equation number 1. Okay, the second step, same thing, go and find your H1, H2 and H3. Okay, remember today we have 2 inlet and 1 outlet, so we need H1, H2 and H3. So H1 will be compressed water, which is HF at 28 degrees Celsius, which is again 117.3. H2, okay, which is from your previous part, which we have calculated to be 2074.12. Okay, H2 is the enthalpy of the wet steam from part A. And of course your H3, which is hot water. Remember, when you see the word cold water, hot water, automatically we assume it to be compressed water. So in this case, it's the same as saturated water at the same temperature, 75 degrees Celsius. Alright, so you have H1, H2 and H3. Okay, now we write our steady flow equation. So steady flow equation has to be slightly modified. Okay, so you see that on the left hand side, in terms of the inlet, there is two fluid. So two fluid, we will need to bring in two of these terms. Okay, then we do our cancellation. So we realize it's a very simple equation, and we plug in the values. So this will be our equation 2. So simultaneously we got equation 1 and equation 2. We can solve it and we will get okay. So if you don't know how to solve the simultaneous equation, please consult your tutor or your respective lecturer. Okay. Okay, so we are ready for the last question, which is slightly more challenging. Okay, slightly only. The steps will still remain the same. So in the hotel, wet and cold water are mixed together. The continuous supply of water, wet steam at a pressure of 5 bar and Jordan's fraction of 0.62 is mixed together with cold water at a pressure of 0.5 bar and temperature of 29. If the mixing chamber is required to produce hot water at a pressure of 5 bar and 70 degrees, determine the ratio of the mass flow rates of the wet and the cold water. So in this case, okay, the ratio that they want us to find is m dot 2 over m dot 1. So this is what we want to know. Okay, whereby m dot 2 is the mass flow rate of wet and m dot 1 is the mass flow rate of cold water. Okay, so with this in mind, we can start the question with the same steps again. So continuity equation m dot 1 plus m dot 2 is equal to m dot 3. So we do not know anything over here. Never mind, just leave it. H1 will be HF at 9 degrees Celsius. Okay. And your H2 will be again your H2 for wet steam. So this wet steam has a Jordan's fraction of 0.62. And the reference pressure is 5 bar. So we go to 5 bar and find out our HF and HG. And of course, lastly, our H3, which is compressed water at 70 degrees Celsius. Okay, so from the table, we'll get this. Okay, so we are ready. Okay, Ken. So again, we will use our steady flow equation. Okay, so after simplification of steady flow equation, you will end up with this. Okay, to save time. Typically for mixing chamber, the steady flow equation will be reduced into this because there's no heat and no work done. Alright, so plug in the values. So this will be equation 2. So how do we solve for the ratio m dot 2 to m dot 1? So we have two equations, but we have three unknowns. Okay, but for our equation, we only need m1 and m2. So what we can do is to replace m3, right? So we replace m.3 with m1 plus m2. Then we rearrange m2 on one side, m1 on one side. Alright, then we will group them, calculate them. So this will be and then we divide across. And this will give us our 0.1037. Okay, so for this question, it will be slightly mathematically challenging. Okay, can. Other than that, it shouldn't be a problem. Okay, let's move on to part B. Okay, so in this case, part B, they give a second scenario. So if 0.6 kg per second of wet steam is mixed with 5.2 kg per second of cold water, determine the temperature of the output. Okay, so we are supposed to determine the temperature of the hot water. So if we know, how do we know the temperature of the hot water? We need to know our H3. H3 will give us the temperature, okay, which is this one. Because we know the output is hot water, which is compressed water. So if you know H3, we know that H3 will be the same as saturated water at the same temperature. Then we need to go to the saturation water and steam table to trace out the temperature that corresponds to H3. Alright, so this is the strategy. Other than that, same steps. First step, m.1 plus m.2 equals m.3. So in this case, m.1 and m.2 is given. So m.3 will be 5.2 plus 0.6. Alright, then next find out our H1, H2 and H3. H1 we have calculated already, 121.5. H2 also calculated already, 1947.58. Okay, and H3 in this case is our unknown. Alright, then again we apply our non-flow steady flow equation. So the equation after simplification will be this one again. Okay, plug in the values. Okay, and from here H3 is our unknown. So we can find out our H3, which is 310.4. Alright. Okay, so we will try to go to the HF column and trace out this value, because the HF that will give this, the corresponding will be the temperature. So we go under the HF column and we try to find. So there is no exactly this value, meaning to say we got to interpolate. So the closest two values are when temperature is 70 degrees Celsius, H is 293. Temperature is unknown, H is 310, which is what we want. Temperature is 75 degrees Celsius, HF is 313.9. Okay, so these values we need to find out our T. So there will be middle minus top over bottom minus top, middle minus top over bottom minus top. Okay, so after interpolating, temperature will give us 74.16 degrees Celsius. Okay, can. So that's all for today. Thank you for going through this tutorial with me very quickly. Okay, can. I'm going through this very fast because one thing is I don't have time. Apologize for this delay. Second thing is I want to show you that this tutorial can be done very systematically. Same for the exam. So please do not throw away the marks for chapter 5. Thank you so much. Good luck. Have fun. See you all again.